Okay, everyone, so here's the second session recorded on Thursday, March 18th. This is to go through the challenge problems that were posted on Husky CT last night. If you are still looking for those problems, on the left-hand side of the page, go down to SI information and click on that, and right on the main page, I believe it's labeled chapters 13 MC problems, or maybe challenge problems are in there. I'm not quite sure exactly how I named it, but it should be right there. It should be a Word document with 15 questions or so on it. Okay, just as a warning, all the slides after this will have answers on them. So if you are not ready for the answers, please look at that Word document that has all the questions with no answers on it, okay? Okay, and again, just my kind of warning that I give every time before going through this challenge problem review. These are the 14 or so questions that I chose for tonight's session to help you prepare for your exam. However, any challenge problems I've given since the start of going over chapter 13 on, all of those challenge problems are equally good to prepare from. You know, it's not like because I put something on tonight's challenge problems that there's a greater chance for it to be on the exam or anything like that, right? In terms of what's on the exam, I don't know anything other than what you know beyond my own experience being around this course. Okay, so again, these problems are a good place to start. However, they do not encompass everything that you necessarily need to know. Okay, so our first three problems are actually a chapter 13 Le Chatelier's principle question. Okay, so we're in an isolated system with two reactants, reactant A and reactant B. Okay, and as the reaction approaches equilibrium, right, meaning as the reaction goes, the temperature of the water decreases. Okay, and again, remember that these reactants are placed within this water system. Okay, it says for the next three problems, state how each manipulation will affect. Okay, so part one says 2 moles of C are removed. Now, product or C is a product. Okay, so typically when we remove a product, we are going to shift towards the product side. Okay, but the kind of caveat or little star to put next to a problem like this is that compound C is actually a liquid here. Okay, so whenever we add or remove a liquid or a solid, there will be no effect on equilibrium. Okay, and that's because when we calculate equilibrium, we don't account for liquids or solids. Okay, so it's only when we add or remove things in the aqueous phase or the gas phase that we will see a shift towards reactants or products. Okay, so again, typically when we if we removed product D, we would see a shift towards products. But here we removed a liquid, which means there should be no effect, right? And that's what this just emphasizes. Okay, how about the next two changes? So 2, the temperature is decreased from 70 Celsius to 45 Celsius. Okay, this is going to result in a shift left, or it's going to shift left towards the reactants, right? That reverse reaction will be favored. That one's a little more complicated, so we'll come back to it in just a second. 3, a catalyst being added should have no effect. Okay, a catalyst allows you to reach equilibrium much quicker, right? Remember, it lowers that activation energy, it lowers the energy barrier, so you can reach equilibrium faster, but a catalyst does not actually shift or affect equilibrium, okay? Again, it decreases the time to get to equilibrium, but it doesn't actually shift equilibrium itself. Okay, so no effect should be for 3. Now, before we address 2, I'm going to go back to the previous slide, just as a warning. Oh, 2 slides, sorry. And let's read the second sentence. As the reaction approaches equilibrium, so as this reaction goes, as A and B combine to make C, D, and E, the temperature of the water decreases. Now, this is alluding to something we kind of went over last semester in chapter 6. Was chapter 6 thermochemistry? Right? And so remember that if this is an isolated system, so if water is losing heat, what's it losing the heat to? Well, it's losing the heat to the reaction, right? The temperature of the water is decreasing, and it's decreasing because the the reaction is absorbing that thermal energy. Okay, so the temperature of the water decreasing is supposed to be a little hint that this is an endothermic reaction, right? Because again, that heat energy is being lost from the water because it's going into the reaction to allow reactants to be converted to products. Okay, so now that we know that this is an endothermic reaction, right, I always recommend that you write heat into the equation. So endothermic reactions have heat as a reactant. Exothermic reactions have heat as a product. Now that we have heat in the equation, we can use the temperature change like we're adding or subtracting reactant, right? So heat is a reactant here, and we are decreasing the temperature, which essentially is like we are taking away reactant. Okay, so if we're removing reactant, we are going to shift leftward to counteract that change. Okay, so because it's endothermic, heat's a reactant, and because temperature decreases, we're going to shift towards the reactant side. If temperature had increased, it would have been like we were adding reactant, which would have caused us to shift to the product side. Okay, but in this scenario, the heat decreased. Okay, and again, this 3 just states that catalyst allows you to reach equilibrium faster, but it doesn't actually shift equilibrium. Okay, now questions 4 and 5 use this chart. So this is a classic chart problem. We're actually missing a lot of data points, but you can use the data points you have to fill out the entire chart. And we're told that this is information based on the combustion of methane to produce CO2 and water, right? Combustion will be a hydrocarbon with oxygen, right? Hopefully you remember these reactions from last semester. So here's the filled in table if you wanted to fill out the whole thing. Okay, but oops, sorry about that. But what's important is this last column, 6 hours, right? So question 4, which we'll see on the next slide, asks for the equilibrium constant. And so there are a couple different ways that you can know that you're at equilibrium. Okay, up here at the timestamps, right, I could have written equilibrium for 6 hours. That could have been one way that I told you it's equilibrium. The other way is actually shown in this chart, where between hours 5 and 6, there are no changes in pressures or concentrations, right? Again, this sort of indicates that you're at equilibrium. Okay, so again, that's another indication. If there is no indication whatsoever in this, like in the chart where equilibrium is, it's pretty safe to assume that your last set of data points is equilibrium. Okay, so even if you didn't know hours 5 and hours 6 had the same data, therefore kind of insinuating we're at equilibrium, it's a pretty safe bet to go straight to hour 6 and find those amounts and know that that would be equilibrium, right? Okay, and so 4 is, what is the equilibrium constant for this reaction? Okay, so the thing about these chart problems is you can fill them out, the entire thing, if you'd like to, but you can also skip from any one step to any other step. Okay, and so what I did here is I actually completely forgot about the entire middle of the chart. I said, I don't care. I have a good feeling that at hour 6, I'm at equilibrium. So I'm just gonna look for my data values at hour 6. Okay, and so I started with my initial and hour 6. So before I actually calculate my changes and find my pressures at 6 hours, I have to first balance my chemical equation. So here's the correctly balanced combustion reaction we're looking at, and it's very important to know that the coefficient of oxygen and water is 2. Okay, so I make this little table of all my reactants and products, and I write the initial amounts. So I start with 0 reactants, and I start with these pressures of I start with 0 products, and I start with these pressures of reactants. Then I'm going to have a change column in the middle, and I'm going to have my hour 6 data all the way to the right. Now, the only data point we know from hour 6 is 2.08. Okay? And so, knowing that, I can use the change to solve for x. Right? So the change for all of these will be minus x if it's a reactant or plus x if it's a product. Okay, but compounds like oxygen and water that have coefficients, those also need to be included. Right? So oxygen, which is a reactant with a coefficient of 2, will have a change equal to negative 2x, while a product like carbon dioxide with a coefficient of 1 will have a change equal to plus x. Okay, so knowing that the change for oxygen should be negative 2x, and I have my initial and hour 6 data, I can solve and find that x should equal 0.66. So I plug that in for x for my other compounds, right? Find the change in terms of numerical value, and apply the change to find the pressures after 6 hours. Okay, and let me just go back to the chart. Right? And so at hour 5, I can see that my pressure of CO2 is 0.66 here. Now, I don't know any of my other 5-hour data points. Okay, but again, CO2 is 0.66. Well, here at hour 6, I can see that my pressure of CO2 is also 0.66. So that can indicate to me already that if the pressure of CO2 doesn't change, that all the data between should be the same between hour 5 and hour 6, which again can confirm that I'm at equilibrium. Okay, so from here I calculate the equilibrium constant. So I do the pressure of my products raised to their respective coefficients, right? So the pressure of water needs to be squared, divided by my pressure of reactants. And again, the pressure of oxygen needs to be squared. When I plug in these data points from hour 6, I get that my equilibrium constant is 0.233, which was answer A. Okay, in question 5, we want to further investigate this reaction. Okay, but in this experiment, we want to create or form 2 moles of hydrocarbon. Okay, and then we're given a bunch of pressures for the compounds, and they say which of the following statements is true, right? And it's obviously a Q versus K problem because that's half of each answer choice. Okay, the big key here is not only is this a Q versus K problem, but this is also a manipulations of K problem, because they say for this experiment, you want to form 2 moles of hydrocarbon, meaning we need to form 2 moles of methane. Okay, and so I'm going to rewrite my equation, and I'm going to multiply the entire thing by 2 so that I form 2 moles of my hydrocarbon. Okay, and so how did I manipulate this equation from our original equation? Well, not only did I flip it, right? My original reactants are now products, and my original products are now reactants. Not only did I do that, but I also multiplied the whole thing by 2. Okay, and so because we did these manipulations, we actually have to solve for the new equilibrium constant, or K tick. Okay, and so because we flipped the equation, we have to take the inverse of our previous K value. And then because we multiplied the whole equation by 2, we also have to square our previous K value. Okay, so the equilibrium constant for this reaction, where we form 2 moles of methane, will be equal to 1 divided by 0.233 squared, which comes out to 18.4. Okay. Now that we know the new equilibrium constant for this adjusted formula, we now want to solve for K to compare the two. Okay, but the big thing to note here is that now it's methane and oxygen that are your products, and water and CO2 that are your reactants. Okay, so when you're plugging these values into Q, you want methane and oxygen in the numerator and CO2 and water in the denominator. Okay, also be wary of your exponents, right? These exponents reflect the coefficients in your adjusted equation. Okay, so we're going to raise methane, we're going to square the pressure of methane. We're going to raise the pressure of oxygen to the 4th power, right? And same thing for the reactants that are in the denominator. Okay, so I plug all these values in, and I find that my Q value is 0.0068, so very, very small, and it is much, much lower than K. Okay, and so because Q is less than K, the forward reaction is favored, right? Because we need more products in order to be at equilibrium. Okay, so this is a little bit less of a traditional question. I tried to combine your classic Q versus K that we've now seen over and over and over again. But here, I actually tried to make you think a little bit by making you calculate a new equilibrium constant because we adjusted the formula. Okay, so hopefully you knew to calculate the new K value. Okay, number 6, which of the following shows the net ionic equation for the reaction between ethylamine, whose formula is given, and perchloric acid? Okay, so at first I just write my reactants, right? Ethylamine is going to react with perchloric acid, okay, and perchloric acid is indeed an acid. So it's going to lose that hydrogen, which is going to go to ethylamine. Okay, so on the product side, I'm going to have the ethylamine plus a proton, right? So now it's C2H5NH3. So it's going to have a positive charge. And then from my perchloric acid, after that hydrogen is lost, it's just perchlorate that's left. Okay, now typically the signs aren't shown here. They would just be shown as a salt together in the aqueous state, but I wanted to show, I think this shows better how this proton was transferred to ethylamine to form these products. Now, if something completely dissociates, we can write it into its respective ions. Okay, so perchloric acid is a strong acid, meaning every molecule is going to split into its ions. So I'm going to rewrite perchloric acid as H plus aqueous plus that's perchloric acid, H plus perchlorate, and that's going to go to our products that we write separate, right? The cation portion and the anion portion, okay, and they're both in the aqueous phase. Now, comparing our two sides of the reactions, right, perchlorate, ClO4 minus, is an ion in the aqueous state on either side, okay? So it doesn't change, meaning it's a spectator ion, okay? So we're going to cancel it out and leave it out of the net ionic equation. And so what is remaining is this, which was the correct answer for the net ionic, right? I believe it was option D. Okay, question 7, hopefully you saw the select all that apply, right? It looks like a multiple choice question, but it was more like select all. And so here it says, consider the dissociation of carbonic acid. Which of the following choices represents the chemical species that can act as a base at equilibrium? Select all that apply. Okay, so it also says can. Okay, so really we're looking for what compounds can act at all like a base. Okay, and so what I did for this is I wrote my two equilibriums out. So focusing on the first equilibrium of carbonic acid, right? We have carbonic acid reacts with water to produce hydronium and bicarbonate. Okay, now carbonic acid is indeed an acid, which means what it reacts with, water, has to be a weak base, right? Acid base. And so automatically we know that water is a base. Well, additionally, right, once carbonic acid loses a proton, on the other end, it forms what we call the conjugate base. Okay, and so in this first equilibrium, we have two different bases. We have water and we have our conjugate base, which is bicarbonate. Okay, and so from this first equilibrium, we have those two answers. Now, as we look at the second equilibrium equation, now bicarbonate's acting as an acid. It's going to be reacting with water, which is acting as a base, to create hydronium and our conjugate base, which is carbonate. Okay, and so from this second equilibrium, we have two bases, water, which we already had before, and carbonate. Okay, and so when they ask to select all that apply, you know, all of them besides carbonic acid can act as a base. Okay, And if you're a little confused, how can bicarbonate be a base and an acid, right? Honestly, water can do the same. And in this case, water is a base in each, but water can also act as a base and acid. Remember, we have a special term for that, amphoteric, which means they can be either an acid or a base. Okay. Moving on to question 8, right? So we have acetic acid. We're putting it into water, and just what is the pOH? So this is kind of a classic question. Okay, so if we have 25 grams, I just labeled it as AA for acetic acid. I use the molar mass to convert to moles of acetic acid, and then I multiply it by 1 over the volume to get my molarity, which comes out to 1.39 molar. Once I know that, I'm going to write my balanced chemical equation. So acetic acid reacts with water to produce hydronium and acetate. I make an ice table and I plug in my initial concentrations. So the only thing with initial concentration is acetic acid with a concentration of 1.39 molar. Now I don't know what my change is, so I'm going to label it in terms of X. So minus X for reactants, plus X for products, and I write my equilibrium concentrations in terms of X. Now that I have my equilibrium values, I'm going to utilize my Ka. So my Ka, which in this case is 1.8 times 10 to the negative fifth, is equal to my concentration of products, X times X, or X squared, divided by my equilibrium concentration of reactants, 1.39 minus X. Now I'm going to use the 5% rule to ignore X, just simplifying my equation. So now in the denominator, I only have 1.39, and I solve for X, and it comes out to 0.005. Now remember, whenever you use the 5% rule, you have to check your answer. Okay, so I took X, 0.005, I divided it by my initial concentration of acid, 1.39, multiplied it by 100, and it comes out to less than 1%. Okay, so it was a valid assumption. This is the correct value of X, and so I'm going to use it to calculate my pH, right? Because X stands for, or also represents, the concentration of hydronium. So my pH is equal to the negative log, my concentration of hydronium, which is equal to 0.005. From that, when I do that calculation, my pH comes out to 2.3. And so I can use the relationship between pH and pOH, right? They always add up to 14. I can use that to pretty quickly find that my pOH is 11.7. Okay. I actually really love this problem. I think it's a great question that your professors definitely could ask tomorrow. Will they? I'm unsure, but you guys definitely have the capabilities to do this, and I think it tests a lot. So which of the following acids is the weakest? Now remember that as the Ka increases, the acid gets stronger and stronger. Okay, so I'm going to solve for the Kas for each of these compounds and compare them to see which one has the smallest or the lowest, because that's the one that will be the weak acid. Okay, so option A was HCl, which is a strong acid, right? That's only one of 6 strong acids. So right away, we can eliminate that, because of course it's not going to be the weakest when it's the only strong acid given as an option. Okay, now choice B, they gave us the pKa, which was 4.7. Now pKa equals the negative log of the Ka. Okay, so using that the pK is 4.7, you're able to find that the Ka is equal to 2 times 10 to the negative fifth. Okay. Now that I have the Ka for B, I'm going to move on to my other compounds. So C, that acid, they gave you the Ka in the problem. They said the Ka was equal to 6.4 times 10 to the negative fifth, right? Which is a bigger Ka than the Ka we solved for in B. Okay, so now we can know that C is not our weakest acid. Now to turn our attention to D, so for the acid that was given as choice D, we weren't given a Ka, but rather a Kb. Okay, so again, we're going to use our relationship between Ka and Kb to solve for our Ka. Okay, so our Ka is equal to Kw, which is 1 times 10 to the negative 14th, divided by the Kb value given. When we solve for the Ka, it comes out to 7.9 times 10 to the negative fifth. Okay, which again, when we compare it to B, the Ka for D is bigger. Okay, so that acid given as choice D is stronger than the acid from part B. Okay, lastly, let's look at choice E, which had the acid had I think it was uric acid, 1.14% ionization. So remember our ionization equation. Percent ionization equals our equilibrium concentration of hydrogen divided by our initial amount of acid times 100. Now here, you need to assume you have some amount of starting acid. So I'm going to pretend we started with 1 molar, right? Because I think that'll make my calculations the easiest. However, you can pick any number. You could have picked 621 molar HA, okay? But again, 1 molar made the calculations easiest, so that's what I did. And so using that, I can find my hydrogen concentration at equilibrium. Okay, and so I find that my hydrogen concentration at equilibrium is 0.0114. And so what I do is I write my ice table for this, right? So HA, which is uric acid, will react with water to produce hydronium and A-. I plug in 1 molar for my initial concentration of weak acid, minus X and plus X, respectively for change. And I find my equilibrium amounts in terms of X. Well, X, which equals my hydronium concentration, has to equal this number, 0.0114, right? Remember, hydronium and H plus are the same thing. Okay, so X equals 0.0114. So I plug that into the Ka expression, and I find that Ka equals 1.3 times 10 to the negative 4th. Okay, and so again, comparing this to my other Kas, it isn't the lowest, right? The lowest Ka was associated with choice B, which is why that's the weakest acid. Number 10, which of the following compounds cannot act as a Lewis base? Right, so remember that a Lewis base, by definition, donates an electron pair. Okay, and so here what I really wanted you to do is kind of understand these structures, and if you drew them out, right, you could see that every choice besides choice D had a lone pair. Okay, so because all the other choices have a lone pair, they have the potential to be able to act as a Lewis base. However, choice D has no lone pairs. Therefore, it can't donate a lone pair. And so because it can't do that, it can't possibly be a Lewis base. Okay, so let's look at some open-ended questions. So this is the first one, and it's a common ion effect problem, right? We're going to have acetate from potassium acetate, salt. We're also going to get acetate from our equilibrium from acetic acid. Okay, and we're asked to find the pH. Okay, so at the very top, I solve for the molarity of acetate from potassium acetate, right? So I use the molar mass to convert to moles, right? And I kind of did skip a step where I converted from potassium acetate to acetate, but that's just a 1-to-1 ratio. And then you'll notice that I divided by 0.3 liters, okay? And it's important, that's kind of tricky, right? I said that there were 200 milliliters of water that potassium acetate was added to, okay? But later on, we added an additional 100 milliliters, and that's of acid. Okay, so the total volume that we're dealing with here is actually 0.3 liters. Okay, so that's what you need to use in order to find your molarity, which comes out to 0.041 molar acetate. Now, in terms of our acid, right, we're gonna actually have a dilution, right? Because we have 100 milliliters of 4.5 molar acetic acid, but we're adding this to 200 milliliters of water, meaning our final volume is 300 milliliters. And so we can use the dilution equation to solve for M2, which is our concentration of acetic acid in the 300 milliliter solution. So when you calculate it, it comes out to 1.5 molar. So what I do is I write my balanced chemical equation. So I have acetic acid reacts with water to produce hydronium and acetate, and I plug in my initial amounts, not just for acetic acid, but also acetate, right? So you have to remember to put the concentration of acetate here. Okay, and just as before, I'm going to write my change in terms of x, so plus x for products, minus x for reactants, and I write my equilibrium amounts in terms of x. Now, I'm looking on the reactant side at the dissociation of a weak acid, right, acetic acid, which means I have to use my Ka, okay, but the Kb was given. So I'm going to find my Ka by doing Kw divided by Kb. Okay, and so I find that my Ka for acetic acid is 1.8 times 10 to the negative fifth. And so I set this equal to the concentration of my products divided by the concentration of my reactants. Okay, and then I'm going to use the 5% rule to ignore x, and I find that x is 6.585 times 10 to the negative fourth, which equals at equilibrium my hydronium concentration. Okay, now I did forget to write my check for the 5% rule. However, it comes out, if you calculate it, to about 0.05%. Okay, so the ignore x was a valid assumption. Okay, so now that I know that this truly is my value of x, which is also equivalent to my equilibrium concentration of hydronium, I can find my pH, right? The pH would be equal to the negative log of that value x. And so what I find is that the pH here is 3.18. Okay, now some students asked me if you could use the Henderson-Hasselbalch equation to solve this problem, and the answer is yes. Okay, if you prefer to use the Henderson-Hasselbalch in this scenario to solve for the pH, that is completely fine. I checked it, you will get 3.18 as well. Okay, and the last question is actually a triprotic acid question, just because I don't know if you've been introduced to this. Again, diprotic acid is more likely to be seen, but you definitely have the capabilities to solve this problem. And so let's work through it. Okay, now what I suggest, especially when practicing these problems, is I don't even look at the questions right away, right? I kind of just look at my equilibrium constants, my initial amounts, and then I come back and answer the questions later. Okay, and so what I do at the start is I always will start with the first equilibrium, right? And I'm going to do one at a time. Okay, so we're going to start with phosphoric acid and react it with water to produce hydronium and dihydrogen phosphate. Now I have an initial amount of phosphoric acid, but I don't know what my change is. So again, minus x for reactants plus x for products, and write my equilibrium amounts. Now this is for the loss or the ionization of the first hydrogen from phosphoric acid, right? So it's going to be equal to our Ka1, or that K1 value. Okay, so our equilibrium constant here is 7.1 times 10 to the negative third, which is equal to our products, x times x, or x squared, divided by our concentration of reactants at equilibrium. Now here I'm going to use the 5% rule and solve for x, which comes out to 0.073. What you'll notice over on the side, though, is that when I perform my check, right, x is actually almost 10%. Which is greater than 5, meaning the 5% rule is not valid, okay? And if you got this value of x, that technically is wrong, okay? It's because the 5% rule isn't valid, I have to go back and solve for x using the quadratic formula method. And so when I solve for x using the quadratic formula, I get two values. I get 0.0695, and I get negative 0.077. However, this negative value isn't possible, because if we plug it in to our ICE table for x, we would get negative concentrations of products, which we, again, just know is not possible. Okay, so that second value is not possible, and x equals 0.0695, which, as you can see, it's not too much different, but it is a different value of x, okay? That is significantly enough different. Now that I know x, right, I solve for x, which is the equilibrium amounts of hydronium and dihydrogen phosphate, I'm going to move on to my next equilibrium. Okay, so here, my second equilibrium is going to be between dihydrogen phosphate will react with water to produce hydronium and hydrogen phosphate. Now, in this ICE table, I actually have two initial amounts. I have an initial amount of dihydrogen phosphate and an initial amount of hydronium. right, you can see their initial amount is equal to the X that we found from our first equilibrium, right, because they were both products in that first equilibrium. Okay, so once I write those initial amounts, I'm going to write my change just as before, minus X from reactants plus X for products. Once I have my equilibrium amounts, I'm going to set it equal to that second equilibrium constant, that K2. So 6.3 times 10 to the negative 8th is equal to my concentration of products divided by my concentration of reactants. Now this time I'm going to use my 5% rule, and I'm going to find that the numbers actually cross out, and X itself equals 6.3 times 10 to the negative 8th. When I do my check for the 5% rule, I don't actually solve for the percentage, but it was something to the negative 5%, right? So a minuscule percentage. It's nowhere close to 5%. So this was a valid assumption, and this X value is correct. Okay, again, now that I found the X value for this equilibrium, I'm going to move on to my last equilibrium, which is between hydrogen phosphate and phosphate, right? The conjugate base being phosphate. Okay, so here's my equation, and I'm going to plug in my initial amounts. Okay, so my initial amount of hydrogen phosphate, right? Hydrogen phosphate's in this second equilibrium, and its equilibrium amount is equal to X. We found that X is equal to 6.3 times 10 to the negative 8th. Okay, now our concentration of hydronium on the next slide is going to be equal to the to this amount, the equilibrium amount of hydronium from our second ice table, right? And so at equilibrium, the concentration of hydronium is 0.0695 plus X, right? But this X value is so small compared to 0.0695 that I'm going to ignore it, okay? And the 5% rule, this check down here, validates that I can ignore X. Okay, so my initial amount for my third ice table for hydrogen phosphate will be that 6.3 times 10 to the negative 8th value. And for hydronium will be that 0.0695 value. Okay, again, you can add to this value 6.3 times 10 to the negative 8th, but again, it doesn't actually affect it because this number is so much bigger than that one. Okay, and we're going to assume that we have 0 phosphate to begin with. So the change, again, minus X for reactants, plus X for products. We get our equilibrium concentrations in terms of X, and we set it equal to our third equilibrium constant, which is equal to 4.3 times 10 to the negative 13th. Okay, so again, I set up this general expression, and I'm going to ignore X here. Okay, so once I ignore X, I can solve and find that my one remaining X is equal to 4.08 times 10 to the negative 19th, which again, when I did my 5% rule, it came out to some percentage times 10 to the negative 10th. Okay, so again, an absolutely minuscule percentage. So this was a valid assumption, and this is the correct value of X. Okay, so now that we've gone through all three separate equilibria, let's look at the questions. So question 12 asked me, what's the pH of the solution? Well, although we add hydronium in all three of our separate equilibria, right, all three separate ice tables, we added some amount of hydronium. The amount of hydronium that we gain from the second and third equilibrium, right, which are these X values, they are so small compared to the 0.0695 value that they're negligible. Okay, and so to find the pH, I just have to take the negative log of 0.0695, which was my X value from that first ice table. When I find that, when I take the negative log of that, I find that the pH is 1.16. Okay. Question 13 asked, what's the concentration of hydrogen phosphate at equilibrium? Well, that's actually in our final ice table, right? It's at 6.3 times 10 to the negative 8th value minus X. Okay, and we found X to be this number here. But this number is raised to the negative 19th, which is so much smaller than 6.3 times 10 to the negative 8th, right? And so this X portion is negligible, again, which our 5% rule, that percentage showed us, it's negligible. And so when you want to answer what's the concentration of hydrogen phosphate, it is at 6.3 times 10 to the negative 8th value. And then lastly, 14, what's the concentration of phosphate? Well, the equilibrium concentration of phosphate is equal to X from this third ice table, which is this value, 4.08 times 10 to the negative 19. Okay, that's all I have. Best of luck studying. Let me know if you have any questions, and best of luck on the exam tomorrow.